Okay, question 7. This is from section 4.1. So first thing we need to do is find out where the vertex of this parabola is going to be. The way this has always been done, at least how I've presented it, is by completing the square. That's not the only way to do it, but because completing the square is something that has to be used later on in chapter 8 material, I'm just going to show the completing the square method. First thing we need to do is I'm going to subtract the 4 on both sides and then factor out this leading coefficient of 3 right here. That's going to leave us with 3x squared plus 2x, and then there's a blank spot here where we need to find a value that completes the square. The way to find that is by taking half of this value, which is going to be 1, and then you square it. It's plus 1. But now we need to balance out the equation again on the left side. So we have to take into account what we've added to the right side. It's not a plus 1, it's 1 times 3, which is 3. So that's what we have to add to this side of the equation, is a plus 3. So now we have the equation y minus 1 equals 3. And then x squared plus 2x plus 1 factors into x plus 1 to the second power. Add the 1 back over and you get y equals 3 times x plus 1 squared plus 1. So in this form, it's clear to see the transformation of left 1 unit and up 1 unit. That's where the vertex is going to be. So left 1, up 1. I need a couple other points on the graph of the parabola to get an accurate width. So if you choose some other x values that are on either side of the x value for the vertex, so the x happens when x is negative 1. So if you choose an x value here and here, you'll be able to get an accurate width of the parabola. So I'm going to let x equal 0. If this is 0 and if that's 0, then those terms just disappear and you're left with 4. So 0, 4. And the nice thing about a parabola is it's symmetric. So that point gets reflected right here. So the parabola looks like that. Question 8 is from section 4.2, polynomial graphs. Now the first thing you want to do is to factor the polynomial if it hasn't been already. This one already has been, but you need to keep in mind that it could be the case that the polynomial given is not factored, and it needs to be in factored form first, because the first thing we got to do is find the zeros and the multiplicity, and the zeros are found from the factors of the polynomial. So in this factor here we see that we have a 0 of x equals negative 1, and from this factor here we see that we have a 0 of x equals positive 2. Zeros are the same as x-intercepts, so I'm going to place those on the x-axis. Now the second thing you're going to want to do is find the y-intercept. To find the y-intercept, you let x equal 0. 0 plus 1 is 1. 1 to the third power is 1. Here 0 minus 2 is negative 2, but negative 2 squared is positive 4, and 1 times 4 is 4. So the y-intercept is here. Now another thing you're going to want to consider is the degree of the polynomial to get the correct end behavior, because polynomial end behavior either acts like a parabola where both ends are going up in the same direction or down in the same direction, or a polynomial graph would resemble a x to the third type graph where the end behaviors are going in opposite directions. So we need to determine the degree of this. Now if it's in factor form, one way you can do that is to add the exponents of the factors. A 2 plus 3 means this is a 5th degree polynomial. If it's already been multiplied out in general form, then you would look for the highest exponent of the polynomial. But when it's in factored form, you just add the exponents. This is a 5th degree polynomial, which means it acts like the end behavior of a 3rd degree. So it's going to have this kind of a shape like that. So I'm going to go ahead and put end behavior here. And here, we got to figure out is what's the behavior of the graph in between near the origin. So as the graph approaches this first 0 right here, the graph either bounces off a 0 or it crosses through. And the way you determine that is by the multiplicity of the 0. This 0 of negative 1 came from this factor right here. that factor appears 3 times, it has a multiplicity of 3. Since it's odd multiplicity, the graph crosses through at that 0. So it now is going to head towards the y-intercept. Now we know it has to cross through the y-axis. It never bounces off the y-axis. It crosses through. But what we don't know yet is, does it turn down immediately, or does it continue to go up slightly before it comes back down? So we need to test a value here in between the y-axis and 2. We have to test 1 to see what the y value is. So if you plug in a 1 plus 1 is 2, 2 to the third power is 8. 1 minus 2 is negative 1, but negative 1 squared is 1. 8 times 1 is 8. So when x equals 1, y equals 8, right about here. So it appears the graph does continue to go up. Then it comes back down towards that 0 right there, and either it crosses through or bounces. And if you consider where this 0 of 2 came from, it came from this factor right here. This factor x minus 2 appears twice. It has even multiplicity, which means the graph bounces off the x-axis at that 0. And it connects up right there. That's from section 4.2. Question 9. This is from section 4.4 and 4.5 really. We studied finding the zeros in both of those sections, 4.4 and 4.5. First thing we need to do is, this is that p divided by q theorem, the rational zeros theorem. So the factors of p are the factors of the constant at the end of the polynomial. So it's plus or minus 1, plus or minus 2. These are all the numbers that divide 18, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Now q are the factors of the leading term, the leading coefficient of the leading term. But since q is just 1, if you divided each of the factors of p by 1, you would end up with the same factor. So this list of p is actually the same as the list of p divided by q, since q is equal to 1. From this list, we choose numbers, use synthetic division to see if we get a remainder of 0. If that happens, that means we found a 0 of the polynomial. So 1, for example, if we wanted to test positive 1, synthetic division, go through the algorithm. 1 times 1 is 1, 1 plus 1 is 2, 1 times 2 is 2. Add the 7 and 2, you get 9. 1 times 9 is 9, 9 plus 9 is 18. 1 times 18 is 18. Right off the bat with our first choice, that doesn't happen all the time, but we got lucky here on the first choice. We found a 0 of the polynomial. So right off the bat, we can partially factor p of x. We know that one of the zeros is 1, so x minus 1 is a factor, and these are the coefficients of a reduced factor, or of a reduced polynomial x to the third, plus 2x squared, plus 9x, plus 18. Now we need to continue the process of choosing numbers from p divided by q, but we no longer have to revert back to the original polynomial for synthetic division. If a factor is a factor of the original polynomial here, it must also be a factor of this reduced polynomial. So whatever number you choose from this list, you can do synthetic division on this smaller polynomial here. So I'm going to test, let's see if I'm feeling lucky. -2. I'm not feeling lucky. I just checked the answer key, so I know -2 is going to work. But you might have to go through a couple of these that don't work in order to find the ones that do. So I'm going to choose -2, but then I'm going to use the coefficients from this reduced polynomial, which are just these numbers right here: 1, 2, 9, 18. And since we have a remainder of 0, that proves that -2 is a 0 of the polynomial, and we have another reduced polynomial, or reduced polynomial here. So the p of x can now be written with 2 of its factors, x minus 1 x plus 2, and then the reduced polynomial x squared plus 9. Now what we have here is a quadratic factor. Once we've gotten it down to a quadratic factor, we no longer have to choose numbers from p divided by q and do synthetic division. We can simply solve the quadratic here for its zeros. Now that can be done in one of two ways, either the quadratic formula, well I guess one of three ways, the quadratic formula, by factoring, or by using square roots. X squared plus 9, if we set that equal to 0, we can actually solve this by taking square roots on both sides. If you subtract 9 and then square root both sides, you get x equals plus or minus 3i. And those are the remaining two zeros. So to answer part A, the zeros were x equals 1, x equals negative 2, and x equals plus or minus 3i. Those are 4 zeros, and we knew we had to find 4 because it was a 4th degree polynomial. Now, part B wants p of x in fully factored form. That means it has 4 factors, so it's x minus 1, x plus 2, x minus 3i, and x plus 3i. Question 10 is from section 4.6. These are rational functions. This has been a topic that's shown up quite a few times on bonus sections of your exams. And it still seems to be a topic that a few of you seem to have gotten, and most of you still need a little bit more practice on this. In the directions here, it says intercepts, horizontal and vertical asymptotes, and then sketch the graph. So within the question, kind of the steps are embedded that you need to do. I'm actually going to do this first, the horizontal and vertical asymptotes, specifically vertical asymptotes first. Those come from the factored form of each of these denominators. So on part A, the denominator would be x minus 2, x plus 2. On part B, I'm going to do these at the same time, part A and B, just so you can see the similarities and the differences. In part B, this would factor into x minus 4 and x plus 1. So back to part A, these factors tell you where your vertical asymptotes are going to be, because the vertical asymptotes represent domain restrictions. X can't be 2, x can't be negative 2, because you'd end up dividing by 0 in that case. So to ensure that x is not negative 2 or positive 2 in this graph, you put a vertical asymptote there, which means the graph doesn't cross through those vertical lines. Over here, we're going to have a vertical asymptote at positive 4 and a vertical asymptote at negative 1 for the same reason. X can't equal those values, otherwise you'd end up with an undefined fraction. So that's a vertical asymptote. Now, the horizontal asymptote are found by comparing the degrees of the numerator and denominator. Here in part A, you see that the degrees are exactly the same, x squared divided by x squared. In that case, you look at their leading coefficients and divide. 1 divided by 1 is 1, so the horizontal asymptote is going through 1 on the y-axis. In this case, part B, this is an x to the first polynomial, this is an x squared, so the degree on the numerator is smaller than the degree on the denominator. If that's the case, the horizontal asymptote goes right through 0. Now, those are the asymptotes. Here, finding the intercepts, that means x and y intercepts. So, to find the y-intercept of part A, to find the y-intercept of any function, not just these, but to find the y-intercept of any function, you let x equal 0. So x equals 0, x equals 0 here, you're going to end up with 0 divided by negative 4, which is 0. So the y-intercept in this is 0. Now over here in part B, if you let this x equal 0 and this x equals 0, you're going to end up with negative 1 divided by negative 4, which is 1/4. So this y-intercept is 1/4, about right there. So those are the y-intercepts. The x-intercepts are found by letting y equal 0. Now we're in function notation, so f of x is the same as y. So if I want to find out where this entire fraction equals 0 and where this entire fraction equals 0, a fraction or a rational expression is only going to equal 0 when the numerator equals 0. So essentially, you're solving the equation when the numerator equals 0 to find the x-intercept. So in this one, you got to consider when does x squared equal 0, and in this one, you got to consider when does x minus 1 equal 0. that's going to tell you where the x-intercepts are. In this case, x squared equals 0 when x is equal to 0, which is where the y-intercept is. X is going to equal, x minus 1 is going to equal 0 when x equals 1. So x equals 1 is the x-intercept of part B. So those are the intercepts. We found the intercepts, we found the asymptotes, now we need to sketch the graph. So you can see with all these asymptotes, these graphs are broken up into pieces. There's a piece of the graph to the right of this vertical asymptote, there's a piece of the graph in between the two vertical asymptotes, and there's a piece of the graph on the left. Now hopefully you've seen these often enough to have an idea in your mind of what these graphs look like. You can't have a piece of the graph here and here at the same time. That's not going to work. It wouldn't be a function because it wouldn't pass the vertical line test. So the piece of the graph is either up here or down here. And because the only x-intercept on this function is here, this piece of the graph can't exist down here. If it did, it would cross through the x-axis, creating a 0 right there, and there is none. For that reason, we know that this piece of the graph must be in this top right corner. We can use a similar argument for this piece of the graph. Either the graph looks like this, or it looks like that, but because there is no x-intercept here to the left side of this vertical asymptote, we know for sure that this piece of the graph needs to look similar to that. Now, in between here, it's best if you just choose some points, because there could be a lot of things happening. Near the origin, the graph can actually cross through a horizontal asymptote. So, I mean, this piece could potentially look like that, or it could, could look like that, or it could be an upside down parabola like that. So we just need to be sure of what it looks like. So I'm going to let x equal 1 and x equal -1 in the original function and see what the values are. So I'm going to write this. If x equals 1, then we're going to end up with 1 over 1 minus 4, which is -1/3. That's about right here. When x equals -1, we actually end up with the same thing. We end up with 1 over 1 minus 4, which is -1/3. So that lets us see the shape of the graph is like that. Now over here in part B, because the horizontal asymptote is right on the x-axis, we actually have to do a little bit more work to find out whether the graph is above or below the x-axis. So if we let x equal 5, for example, and you plug it in, I'm actually going to get it back into factor form. So if x equals 5, for all of these x's, you end up with 4 divided by 5 minus 4 is 1, 5 plus 1 is 6, 1 times 6 is 6, you end up with 2/3. So when x equals 5, y is 2/3, which is about right here. Now that one point is sufficient to determine where the graph is, because one point of this is above the x-axis. All the points must be, because if there were a point here, and then if we were thinking that some of the points could be down here, then the graph would eventually cross through the x-axis somewhere, and it doesn't because there's no 0 right here to allow the graph to pass through the x-axis. So that piece of the graph looks like that. Now, skipping the middle for a second, if we come over here to the left portion, we need to test what happens when x equals -2. So when x is -2 minus 1, that's -3. -2 minus 4 is -6. -2 plus 1 is -1, but that's +6. That's -1/2. So when x equals -2, we're at -1/2. And for the same reason, the whole entire graph has to reside underneath the x-axis. At least this piece of it, it can't cross up through because there's not a 0 over here to allow the graph to cross through the x-axis. Now, between this point and this point, we know the graphs must be connected. As this piece of the graph nears this vertical asymptote, it has two options. Either it goes up to infinity or it turns down to -infinity. But we know it can't turn down to -infinity because it would eventually have to cross through the x-axis. and there isn't a 0 there, so that piece of the graph looks like that. If you tested x equals 2 in the original function, you would see that 2 would generate a negative value for f of x. So this piece of the graph comes down like that.